Homogeneous ordinary differential equations. This video is going to be going through one way to solve second order ODEs and first order actually, where the right hand side is equal to 0. This means they're in the form dy by dx, d2y by dx squared plus p dy by dx plus q of y is equal to 0. Here we could have a coefficient of d2y by dx squared that would be 0, in which case it's a first order ODE. So to solve this, the first thing we're going to do is have a look at the auxiliary equation. So this is an equation that we are creating to help us solve the ODE. If we let d2y by dx squared be represented by lambda squared here, dy by dx be represented by lambda, and y be represented by 1. Then we can put in our coefficients. So add in p, q, and the right hand side is 0. So now this equation, we want to find out what lambda is. So the easiest way of solving a quadratic is to factorize. So we're going to have our two brackets. That's going to be equal to 0. We're going to have our lambdas, and then we're going to have our two sections of the bracket. I'm just going to call these alpha and beta, two constants here. So our roots to the equation, lambda is going to be negative alpha and negative beta. If we have two distinct roots here, so alpha does not equal to beta, or negative alpha does not equal to negative beta, and alpha and beta are real constants, then our equation, our general solution to the ODE, will be a constant multiplied by e to the negative alpha x, negative alpha being our first root, plus c2 e to the negative beta, don't know why it's done that, e to the negative beta x, and that would be our general solution for two distinct roots. If, for example, we had two roots which are not distinct, so two roots that are the same, say we had lambda equal to, let's say alpha again, then what we would do is our general solution would be c1 e to the alpha x. Here this is alpha. In the previous bit it was negative alpha, hence why it's negatives in here, just as a quick cover over that, plus c2 x e to the alpha x. So we would take our first root as usual, and then the second root would be used, but we would multiply e to the lambda x by x to make it slightly different. So what would we do if we had lambda is complex roots? So here we're going to have lambda equals alpha plus beta I, sorry, plus or minus beta I, because there'll be two roots being a quadratic here. Here this would be alpha and alpha. So yeah, complex roots, we would have y equals c1 e to the alpha x sine beta x plus c2 e to the alpha x cos beta x. And that would be our general solution for complex roots. Now it doesn't matter if you have plus or minus beta in here, because for sine it would not matter, and for cos, this is then taken into C2. So C2 being a constant can be either positive or negative. It's just worthy to note here that C1 and C2 are complex constants. They don't have to be real. So now we are going to go on to a quick example. Go back to over here. So our example is going to be 4 dy by dx squared, d2y by dx squared, plus 32 dy by dx, plus 28y is equal to 0. So the first thing to do is to put it into a form that we can work with. So if we divide everything by 4, we can get rid of this coefficient of d2y by dx squared. So we're going to divide by 4, so that will cancel. That will go divided by 4, that will be divided by 4, and the 0 divided by 4, which is 0. So now we can have a look at our auxiliary equation. Lambda squared plus 32 over 4 lambda, which is 8 lambda, plus 28 over 4, which is 7, equals 0. To solve this, we would have lambda plus 7 and lambda plus 1, which would mean that lambda is equal to negative 7 and negative 1. Working with these two values for lambda, we can see that there are two distinct roots, which means we are putting it into the form y equals c1 e to the alpha x plus c2 e to the beta x. So our answer will be y equals c1 e to the negative 7x plus c2 e to the negative x. And that was homogeneous ordinary differential equations. Thank you for watching.